Okay, honors chemistry people, we are going to start a new chapter today. We're going to start looking at how these atoms bond. Now that we have the electron patterns down, it's really easy to figure out how atoms bond. There are two broad classes of chemical bonds. Those that bond atoms or ions together within a molecule or a solid are called intramolecular bonds. Intra in Latin means within. So intramolecular bonds are those bonds that are within a molecule, within a compound, okay? Those that bond molecules to other molecules are called inter. Inter in Latin means without or outside. So intermolecular. And we will deal with intermolecular bonds in a later unit. So this unit is all going to be about intramolecular bonds, or the bonds within individual compounds, within individual molecules. Okay? So, ionic bonds. There are two main types of intramolecular bonds. Well, actually, there's three. We have ionic bonds, we have covalent bonds, and we have metallic bonds. We're going to spend a lot of time talking about ionic bonds and a lot of time talking about covalent bonds. We are going to spend a little bit of time talking about molecular or metallic bonds. So the first thing, in order to figure out ionic bonds, we have to figure out ions. And I've introduced ions to you a little bit before. We're going to talk about how positive and negative ions are created, okay? So a positive ion forms when an atom, let's see, how would I make things positive? I would have to lose electron, right? So a positive ion forms when an atom loses one or more valence electrons in order to obtain a noble gas configuration. We are going to lose those valence electrons to get back to a noble gas configuration. A positively charged ion is called a cation. Here, let's put that actually on the line. It's going to let me erase. A cation. Now, I know that in normal English terms, we would call that a cation, but in science, we call that a cation. So cat means positive, cathode. You might have heard like the cathode end of a battery, that's the positive end of the battery. A cation is a positive ion. To understand the formation of a positive ion, we're going to compare the electron configurations of the noble gas neon, atomic number 10, and the alkali metal sodium, atomic number 11. So we have the electron configurations of neon. We have 1s2, 2s2, and 2p6, complete full valence electron shell, right? Neon, we've got all 8 valence electrons. But when we look at sodium, we have this. We have 1. So remember, we are always trying to get a noble gas configuration. So my question is, neon already has it. So sodium, we have 2 options to get a noble gas configuration. I can add 7 more electrons, or I can lose, or I could lose 1 electron. What would be easier? I think losing this 1 electron is a lot easier than adding 7 new electrons. So the 1 electron that we're going to lose, of course, is going to be the valence electron. So if I lose that valence electron, that 3s1 electron, that sodium now has a +1 charge because it has 1 more proton than it has electrons. But notice the electrons I am left are the same as neon. So I have acquired a noble gas configuration by losing that valence electron. Okay, so note that the sodium atom has one 3s electron. It differs from a noble gas by that one single electron. When sodium loses this outer electron, the resulting electron configuration is identical to neon. So when we lose valence electrons, we are always going to lose them in a bid to create a noble gas configuration, which will give the element some stability. So here's the big idea here. Profundity. Metals tend to lose electrons to form cations or positive ions. Okay, so metals always lose their valence electrons to create positive or cations. Okay, metals from group 1 always form +1 ions. They have one valence electron, so they lose that one valence electron to go back to noble gas configuration. Metals from group 2 always have a +2 because they have two valence electrons. It's a lot easier to lose those two valence electrons than it is to gain 6 electrons. So they lose those two valence electrons to go back to a noble gas configuration. Okay, there are a couple transition metals that have set charges as well. Silver always forms a +1. Zinc, oh my gosh. Zinc always forms a +2. And I would also say cadmium always forms a +2. And aluminum always forms, well, let's erase that. That's not what I wanted to write. Aluminum always forms a +3 or a 3+ ion. Okay? Now, so we have now designated group 1 and group 2. Remember, group 1 are the alkali metals, or the very first column in the periodic table. And the group 2 are the alkaline earth metals. You might want to grab a periodic table and start coloring this in, okay? All other, in fact, we should probably do this. Let's grab a periodic table. So let's get into our periodic table. And let's open this up. So let's highlight these. Let's draw. Let's just start with our highlighter. So group 1, here we go. Group 1, let's see if we can get this on frame. Group 1. This whole group right here will give us +1, okay? So we are going to label these guys +1. So they will give us a +1 charge. Let's do our group 2. Let's change our color here. Group 2, these guys will give us a +2 charge. So let's change our pen. Let's do blue. These guys will give us a +2 charge. And then we have a couple of random ones that have set charges. Let's highlight these guys in green. Okay, so silver is going to be a +1. Let's put that in green. It's going to be a +1. I'm going to just circle that +1 there. Cadmium is, it says it's a +1, but it's always a +2. So let's put that in green. That's a +2. Zinc is always a +2. So I'm going to just circle that +2. And then aluminum is always a +3. It's guaranteed all the time. So aluminum is always a +3. Okay? So there are some charges on the periodic table. We're going to fill in some more as we go along. Okay? Now, the thing is, the transition metal groups can have more than one positive charge, and their charges need to be given. For example, iron can be +2 or +3. So let's look at how that happens. Now, if I do the configuration for iron, beyond iron, beyond argon, I will have 4s2 and 3d6, right? 1, 2, 3, 4, 5, 6. 3d6. So let's put that out there. So I will have 4s. Oh, why does it move on me? Okay. 4s2. And then I have 5 orbitals in 3D and 3d6. 1, 2, 3, 4, 5, and 6. Okay, so this is our orbital notation for the valence of iron. So to create the +2 charge, the valence electrons go. These electrons go away because those are the outermost ring. Those electrons go away. So if those electrons go away, that creates us the iron +2. Now, remember when I said that these sublevels are incredibly stable when they're exactly full or exactly half full? Is there a way that I can make this 3D sublevel exactly half full? There is. So if I do this, if I take this electron and I take this electron away, that 3D sublevel is exactly half full. These valence electrons out here, the s electrons, are already gone. So I have 3 electrons that I am now missing. So this will create the iron +3 ion. Okay? Now, for copper, we will have something similar going on. Let's do this. We will have 4s, 1, 2, and 3d. Let's see, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we can have the valence electrons go and leave. That will give us our copper +2. Or remember when I said things are super stable when they're exactly half full? Remember this? Whoa, I don't want that thick. Let's make this a little bit thinner. So let's redo the 4s. 4s up. 1, 2, 3, 4, 5. 3d. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I take one of those electrons from the 4s and promote it up there, that gives this 4s sublevel exactly half full, and this gives me my 3D exactly full, which creates it an even more stable copper. But then to create that ion, if I take this electron from the valence shell 4s and remove it, I'm down 1 electron. So that will create my copper +1 ion right there. Okay? And tin can do the same thing. We can have a +2 or a +4 on tin. So in order to understand what charge these transition metals or the metals in the D block have, we actually have to put Roman numerals in there to designate what the charge is when we are writing out the name of these. Okay? Nonmetals, though, which are located on the right-hand side of the periodic table, they have high electronegativity and high electron affinity, so they easily gain electrons to obtain a noble gas outer electron configuration. Okay? Think of it this way. To obtain a noble gas configuration, chlorine gains 1 electron. So if I look at chlorine, I'm just 1 electron and that 3p5 away from being 3p6 and having a full valence shell. Because chlorine, as it is right there, has 7 valence electrons. So if I add 1 more and create the 3s2 3p6 with a -1 charge, you'll find that chlorine has a full valence shell, which gives it a noble gas configuration like argon. Okay, so it will have that noble gas configuration just like argon. So that's what chlorine will do. Think of it this way. Is it easier for chlorine to gain 1 electron, like it did to be like argon, or to lose these 7 valence electrons to be like neon? I would say it's a lot easier to gain 1 electron than to gain 7, or than to lose 7. Okay? So the chloride ion does end up having the exact same configuration as argon, just because it is the noble gas configuration that is easiest for it to obtain. Okay. So an anion is a negatively charged ion. So think about cation being positive. Cathode is the positive end of a battery, and anode is the negative end of a battery. An means negative. Anion is a negative ion. So to designate an anion, the ending "ide" is added to the root name of the element. So chlorine, the root of chlorine is chlor, so we're going to call it chloride. Fluorine, the root of fluorine is fluor, so we're going to call it fluoride. Thus, the chlorine atom becomes the chloride atom. What's the name of nitrogen? What's the root of nitrogen? Nit? Yep, nitride. It's frustrating. Nitride. If I can write this, it would be awesome.